आज म बीएससी फर्स्ट इयर फिजिक्सको चाहिँ नोट लिएर आएको छु। यसलाई चाहिँ यो भिडियो चाहिँ अन्तिमसम्म हेरेर चाहिँ नोटलाई कपी गर्नु होला। एन्ट्रोपी जनरली एन्ट्रोपी मिन्स द मेजर अफ डिग्री अफ disorder of molecule of the system. Literal meaning of entropy is transformation. The concept of entropy was first introduced by Clausius in 1854 while working on the formulation and application of the second law of thermodynamics. Now the entropy of a system may be defined as the function of thermodynamical variable PBTU, and its change between two states is the integral of dq by t between the state along any reversible path joining them. Mathematically, ds equal to dq by t, dq equal to t ds, where dq equal to the quantity of heat absorbed or reject at temperature, tds equal to change in entropy. Similarly, the change in entropy in passing from one adiabatic to another adiabatic is integration s1 to s2 ds equal to s2 minus s1 equal to integration a1 to a2 dq by t. For adiabatic process, dq equal to 0. Therefore, ds equal to dq by t equal to 0 by t equal to 0, or ds equal to 0. On integrating, we get s equal to constant. Thus, entropy of a substance or system is that physical quantity which remain constant with the substance undergoing reversible adiabatic process. Unit, it is measured in joule per Kelvin. Physical concept of entropy. Generally, it is difficult to interpret physically the concept of entropy as there is nothing physical to represent it and it cannot be felt like temperature or pressure. Simply, entropy means the measure of the degree of disorder of the molecules of system, and change in entropy is change in entropy equal to heat added or subtracted divided by absolute temperature, that is ds equal to dq by t. From above expression, we may say that heat energy has the same dimension as the product of entropy and absolute temperature. Since the gravitational potential energy of both is proportional to the product of its mass and height above some zero level, hence if we may take temperature measure from absolute zero equivalent to height, then we may take entropy as analogous to mass or inertia. In this way, we may think of entropy as interthermal inertia which bears to heat motion. Expression of entropy of system. Let us consider I1, I2, I3 are thermodynamical as at temperature T1, T2, T3, etc. as shown in diagram. Hence, here A1 and A2 are adiabatic. Consider a Carnot reversible cycle efficiency. Let Q1 be heat absorbed at temperature T1 from A to B. Q2 is heat rejected to at temperature T2 from C to D. Now, from definition of efficiency of Carnot engine, eta equal to 1 minus Q2 divided by Q1 equal to 1 minus T2 divided by T1. Q1 divided by T1 equal to Q2 divided by T2. That is an equation first. Again, considering reversible cycle DCEF, let Q2 is heat absorbed at temperature T2 from D to C, and Q3 is heat rejected at temperature T3 from E to F. Then we make Q2 by T2 equal to Q3 by T3. Let us equation number 2. From equation number 1 and 2, we can write Q1 by T1 equal to Q2 divided by T2 equal to Q3 divided by T3 equal to constant. In general, if Q2 be the amount of heat absorbed or rejected at temperature T in ongoing from one adiabatic to another, then Q divided by T equal to constant. This constant ratio is called change in entropy, represented by two adiabatic. If two adiabatic lie very close to each other and dq with a small amount of heat absorbed or rejected at temperature T, then change in entropy is given by ds equal to dq by T. Let equation number 3. Suppose S1 and S2 be entropies represented by two adiabatic S1 to S2 ds S minus S1 equal to integration of A1 to A2 dq by T, This is an equation number 4. This equation third and fourth are the required expression of change in entropy of substance. Entropy in reversible process. Let us consider a reversible Carnot cycle ABCDA. On moving A to B, Q1 amount of heat is absorbed at temperature T1. The increase in entropy of working substance is Q1 by T1. The entropy of source is decreased by Q1 divided by T1 on moving C to D. Isothermal comparison, Q2 amount of heat is released at temperature T2, so increase in entropy in sink is Q2 divided by T2. On moving from D to A, the entropy remain constant. Change in entropy equal to Q1 by T1 equal minus Q2 divided by T2. Equation number 1. Also from Carnot reversible process, Q1 divided by T1 equal to Q2 divided by T2. Change in entropy in first equation is Q1 divided by T1 minus Q2 divided by T2 equal to 0. This equal to 0. Hence we can conclude that the change in entropy of any reversible process is 0. That is, there is no change in entropy of the reversible process. Entropy in reversible process, irreversible process. Entropy in irreversible process. Let us consider an irreversible process and Q1 be the amount of heat absorbed at temperature T1 and Q2 be the amount of the heat at release at temperature T2. Then efficiency of reversible process is given by eta I equal to 1 minus Q2 divided by Q1. But for reversible process, efficiency is eta R equal to 1 minus T2 divided by T1. As we know, eta I means irreversible process is less than eta R means reversible process. 1 minus Q2 divided by Q1 is less than 1 minus T2 divided by T1. Q2 divided by Q1 is less than greater than T2 divided by T1, as Q2 divided by T2 minus Q1 divided by T1 is greater than 0. Change in entropy of reversible process is always positive. Next day we will discuss TS diagram. Today is enough so that I will